Hey folks, this is Captain Jones here to talk to you about the calculator program from Chapter 10. This is a doozy. It's an awesome one to analyze. I really hope you get into it. My objectives today are to sort of introduce this program to you. So we're going to take a look at the flowchart for what the authors came up with. And I won't go through it piece by piece, but there's a couple of important things that are new to us in this program that I want to talk about, which are, number one, how to convert integers in this range to their ASCII values and back again. That's kind of a unique thing in this chapter that I want you to be able to understand. And then the actual calculator program itself uses something called Postfix Notation, so I'll describe what that is to you so you understand kind of how the program works. And then after you go read Chapter 10, hopefully at that point you'll be able to trace a very large LC3 program that demonstrates everything we've talked about so far: sequential decomposition of a problem statement, the use of hardware I/O, and stack-based arithmetic. So let's dive in. Okay, so here, if you take a look, this is the flow chart from Figure 1014. This is kind of the overall flow chart for the calculator program. And so you can see that after some initialization, what we're going to do is get a character from the user. It could be one of these symbols that indicate to do something specific in the calculator, or it might just be an integer, in which case we sort of will convert that to a binary value and then prompt the user for the next number or symbol in the arithmetic sequence that they want operated. Okay, so let's start low. Actually, let's start low level, and we'll take a look at the functions that do ASCII to binary, binary to ASCII conversion. So hopefully you recall from, or actually you might not have seen this, but the lesson on strings that we can use ASCII characters to encode letters and numbers, and there was kind of a useful thing here. Related to the ASCII values for digits, that you might notice that for every digit, the ASCII value was hex 30 greater than that integer digit. So an easy kind of conversion was, if I've got an integer and I want to get to the ASCII value, I add hex 30. Or if I want to have the ASCII value and I want to go to the integer, then I subtract hex 30. Similarly, the way the actual calculator program uses is it just sort of masks off. It just sort of eliminates the upper 4 bits. So you can see if I just sort of cover my hand over the 3 here, I get 0. So let's see. Okay, so in converting ASCII to binary, I've got my ASCII characters stored in memory here. 3 is ASCII hex 33, 1 is ASCII hex 31, 7 is ASCII hex 37. I've got my null terminator that marks the end of that string. So converting this into an integer amounts to masking off the top 3. So I'm just keeping the lower bit here. In this case, hex 33 becomes hex 3, hex 31 becomes 1, hex 37 becomes 7, and then I just multiply by the correct value of 10 and add them up. So this first value, I multiply by 100. The second value I multiply by 10. I add the ones digit to get the value 317 in base 10. The figure 1016 has the full ASCII to binary conversion. There's a couple of details I'm leaving out here in terms of handling negative numbers and checking for overflow and stuff like that. I'd encourage you to look at. I would encourage you to look at in this full code. But the crux of the conversion is this process here. Where we are, masking off the ASCII, the upper nibble, and multiplying by the correct value of 10. The other program to go from binary to ASCII is to me also very ingenious. But the process of this is to start by subtracting values of 100, and every time we subtract a 100, we increment some register by 1. And it's when we subtract enough 100s that basically our value is smaller than 100, then that is a count of how many hundreds are in this number. So we subtract 100 3 times. That 3 then is added to hex 30 to be converted into the ASCII value for 3. The result of this, when we sort of subtract 300 is 17, so then we do the same process, but subtracting tens. We're going to subtract as many tens as we need to until the subsequent value is smaller than 10, incrementing some sort of temporary variable the whole time. And in this case, once we subtract off just a single 10, then we're left with our ones place, and so the integer value 1 is sort of the output of this for the tens place. We add hex 30 to that to get the ASCII value for 1, and then whatever ones place comes out, we convert to ASCII in the same fashion, and we finish by inserting our null character at the end to mark the end of this ASCII string. Again, I'm leaving off a couple of details in terms of how we handle negatives and that sort of thing, so I'd encourage you to look at figure 1019 to see those details, but the crux of that algorithm works like this. Okay, let's see. Let's talk about postfix notation. So this is also known as reverse Polish notation. This is an alternate way to express mathematical expressions that has a couple of benefits. So the format that we're used to is called infix, where I've got the operation that I want to be performed on my numbers inserted in between the first and second number. So, in this case, 2 plus 3 is the expression for the value 5. 2 plus 3 times 4 is a mathematical expression in which I would have to evaluate 3 times 4. First, we would use the acronym PEMDAS to identify the fact that the multiplication operator has a higher precedence than addition. So I would do 3 times 4 first, that would be 12, and then I would perform my addition. 2 plus 12 is 14. The one kind of catch to infix, I mean, we're very used to this, but the problem is that the precedence of these operators matters, right? If I, or in other words, if I were to put parentheses around the 2 plus 3, that would change the result of this expression because I'm forcing a different order of operations than sort of is natural for this notation. In postfix or reverse Polish notation, I place my two numbers first, and then after them I place the operator that I want performed on them. So to sort of rearrange this expression 2 plus 3, I would write 2, 3, my two numbers, and then the plus sign afterwards. So this means, effectively take the most recent two values and add them together. Reverse Polish notation for this expression looks like what you see here, meaning I am going to start with my 2. The next value I want to be the result of this multiplication. So you can imagine this little box around the 3, 4 times, which is telling the postfix evaluator to do the 3 times 4 first, and then to add the result of that to the variable 2. It takes a little bit to kind of wrap your mind around, but the nice part of this this notation is that we don't need parentheses. We can unequivocally express the order that we want our operations performed in using reverse Polish notation, because we just need to perform that whatever operation we see on the two numbers that are immediately preceding it. So by way of example, let me pull up, see if I can pull up the stack simulator, because the reason the authors are using postfix notation is that it is ideally suited for a stack. So I'll show you why right now. Okay, so this is our stack simulator. What I'm going to do is sort of simulate this expression here, where I'm multiplying 3 by 4 and then adding it to the value 2. And when the symbols come in this order, the only thing I need to keep in mind is just that whenever I see an operator, I always perform it on the two most recent values. So if I start here, I'm going to push the value 2, push the value 3 onto my stack, push the value 4. As soon as I push this multiplication operator, then that's the cue for this calculator program to take a look at the two most recent values and multiply them together. So what I'm going to do is sort of pop that stuff off the stack. 3 times 4 is 12. So the result of that then gets pushed onto the stack. What comes after the multiplication operator is the addition operator. So I'll push that onto my stack. The calculator program sees this operator, and then it performs the addition on the two most recent values. So I'll pop this all sort of off the stack, and in place goes the value 14. And so that's how the calculator program is going to sort of evaluate this sequence of numbers and characters to get to the correct value. You can see a couple examples here of converting what we would call sort of like normal, mathematical expressions, infix expressions, into postfix or reverse Polish notation. The book talks a little more about that also. Let's see, I think it's, where is it? Oh, you can see it. Yeah, you can see an example here in section 10.3.1 of converting this expression into postfix. And this actually also kind of shows you, where you're hitting the enter key and how you enter the D to indicate that you're done and want to see the result. Okay, so that's all I'll show you about this program. The last thing I'll just say is definitely, again, I would recommend you to look through this, particularly all the little subroutines here that clear the stack or do the addition operation or the multiplication operation. There's a lot of great stuff in there that are performing range checking, checking your input values for correct integers, and you're not typing letters, and checking for overflow. So there's some great examples in this chapter of how to write code that decomposes well, that is organized well, and is robust. Is able to handle erroneous values. So lots of great code in here. To recap, this calculator program follows this major flowchart with these boxes here kind of being their own subroutines that you can read in chapter 10. Converting from ASCII to binary just involves taking each of our ASCII characters, masking off the top nibble and just keeping that lower value and multiplying by the correct power of 10. Converting from binary to ASCII involves subtracting off first 100s until we get a value that's less than 100, subtracting off 10s, and that gives us our respective hundreds, tens, and ones digits that we can then add hex 30 to get to the ASCII value. And then we talked about the postfix or reverse Polish notation, where I place the operation that I want performed on my two values at the end of the sequence. And this notation is perfectly suited for use with the stack. So that's exactly what the calculator program does, is as values and operators are pushed onto the stack, entered by the user, then they're effectively pushed onto a stack. And anytime an operator is encountered, then the calculator program just sort of pops the two most recent values off the stack and performs the operation on them, just like we saw in that little demo. All right, folks, that's all I got. I'll see you next time.